So just like we saw in the movie, so we're going to swerve off the path and talk about magnetic fields because moving charges produce magnetic fields, just like you saw in the movie with Faraday and Einstein and all that. And so this statement here, let's just unpack this first statement. The net motion of the immobile electron C in equilibrium is zero. So in equilibrium, electric field is zero. So basically that would just be that, going back to that picture of, imagine a bunch of people in their inner tubes waiting for somebody to open the floodgate. They're just kind of bobbing there in the sea. There's this motion that you can't just have no motion, but you have effectively no motion. The average of all that just sitting there bobbing would be zero, because it's basically random motion. But as soon as that field's applied, it tilts that out of whack. And so if you go back to those other simulations, the Russian dude on YouTube, remember you apply a voltage, that's like raising, the hill. All of a sudden I have a ramp and stuff's going to fall down it, to use the gravitational metaphor or analogy for that. And so these charges get moving, and our gauge here, we're looking, if you look at this line, current flow is how many moving things go past the line in the sand every second. That's ultimately going to be our definition of current flow, electron current. So we're imagining this flow of electrons, pretending that it's orderly. And so here is this definition. Electron current, little I, number of electrons per second that enter a section of a conductor, meaning the stuff past that line in the sand, if you will. How many electrons per second? So if we could stand there and count them, okay, which we count them indirectly by other means. We obviously don't see them in that regard. But we can infer how many are based on the structure of the metal, the electric field applied, et cetera, et cetera. So we have this thing that we just finished talking about, voltage, which is electric potential, or the difference in electric potential. And if you think back pre-spring break, I know that is, you've lost all of that over spring break, okay, is related to this energy balance, okay? The sum of kinetic and potentials are going to be zero. So we're kind of a little bit of review here to tie it all together. But kinetic energy, changes in kinetic energy produce changes in speed, okay? And changes in potential energy upset the balance of all the energies, which means there's a change in kinetic, okay? So if all of a sudden you're at the top of a hill, your potential to move just increased, and you're likely to move if you're free to, all right? So we just realized in this last thing that there was a speed associated with the electric field. And so that means electric fields produce a change in kinetic energy. They have to, because this electric potential difference is getting something moving. So we wouldn't need necessarily to show that there's a velocity term in some equation. It must be true, but how you come to that really doesn't matter as long as you come to that. And so we have this right here. They're all related in this formula. Voltage is potential energy per unit charge and we just have that or times the distance. And so why is that true? Well, electric field will be force per unit charge. Okay? So let's, oops. So remember, electric field is force per unit charge. And if I multiply that times the distance, then I have the potential energy, or the work done. So remember, W, big W for work, force times distance, same thing as potential energy. So that's why that's true, is because if you apply the definition of electric field, you have force times distance with that R added in there. So just kind of throwing some review items in to connect dots. And so now, if you remember, so let's right up here. All right, so our if I take this, E would be V bar per electron mobility, or right there. So if we just take our drift speed equation, drift speed of an electron equation, solve it for the electric field, put it into our voltage equation that relates the electric field to the potential energy, then we come up with this new twist on the formula. For understanding the electric field in a different way. Because prior to today, the electric field was force per unit charge. Now I can talk about the electric field in terms of the average speed of the electrons, their mass, their charge, and the average time between the collisions. That's a different viewpoint. It's it's closer to ground level, if you will, because these are the things that are actually directly related to the motion of these particles, whereas force is just sort of this, it's this thing that we believe exists, even though it's not stuff, but we talk about force. But now I can talk about electric field in terms of without using force. Okay, that's because that's buried in the drift speed equation, which was from the momentum principle, which is force. The time rate of change of momentum is what force is defined according to Newton's second law. So we've written out the force variable, but that's what this is the structure of force. Ultimately, that V me per delta t, that's force. Because this right here, that would be force. Okay, because electric field is force per unit charge. And this right here, that's the charge, fundamental property E. So we just have a new version of force. But doesn't that make sense? Isn't a V per T, isn't that just going to be an A, acceleration? And I have a mass of the electron, so I really have F equals ma in this part. That V per delta T is an A and the M is an M. I have ma right there. But I have Newton's second law in terms of all Coulomb stuff. So that's another thing about these developments, is that they give us back these known things, and we're satisfied. We're more satisfied that this is a good picture because it boils down to something that's undeniably true elsewhere. All right, so a little bit that there. So this statement, we sort of already said this, but it's worth kind of trying to condense it here. So electron drift is dealing with a never-ending set of collisions between mobile electrons and positive atomic cores. So what is electron drift? Well, it's that. And we have a formula that accounts for that. Because there's all of these collisions, okay, all these continuous collisions involve a great deal of heat, namely through the average kinetic energy of the particles. Because the average kinetic energy of the particles is dealing with speed. More particles colliding at any number of speeds, more heat transfer. Right? So if you've ever maybe put too many extension cords together, you'll notice they get hot. Or if you're using, say, a weed whacker or a leaf blower and you don't have a high gauge, a really thick cord, you're drawing too much current through a thin cord, it gets hotter faster. Eventually they're all going to get hot, and the longer they are, the bigger the draw that it has to do to get it through there. And so if you've ever felt a hot wire from that sort of thing, you felt electron drift getting out of control. You felt the result of the average kinetic energy of all of these drifting electrons. Okay, so, and what's interesting in a metal is as it gets hotter, its resistance goes up. So its resistance goes up, which makes it get hotter, which makes its resistance go up, and eventually it just would melt or become not really a conductor anymore. It'll short out. This part here, maybe not obvious. That heat, the more you could just think of it in terms of the chaos of it all, the more frenetic this whole thing, this vibrating mass of metallic crystal structure, the cores vibrating, and more speed, you have more and more things banging into each other, and meaning it's sort of like the difference in the room here. You know, you could run across the room and there's nothing in the middle. If I put a couple things in the middle, it'll slow you down. If I put more things, it'll slow you down eventually. And then if we could have people at the edge that were just constantly pushing things back and forth, you know, then you would really get slowed down because you wouldn't see stuff coming, if you will. And so that so ultimately it limits the speed of the electrons, and it gets to a maximum drift speed in that regard. So that's just some of the side of these things. All right. This gets us right to that movie. The part of the movie dealing with Faraday. They did this. You saw them do it in the movie, and that was a reenactment of what they actually did. In fact, those toys that you saw in the movie, that's actually we could remake those same things, but those are what you saw there is just that they actually had that exact same thing way back when, and they did it that way on a table like that with compasses like that, with batteries like you saw them hooking up and whatnot. And so we could do the same thing. We could lay a wire across a compass and juice it up and watch the needle of that compass deflect. Right? And so we'll get to that in some experiments soon enough. But it is a fact, as stated here, electron current produces a magnetic field that will deflect the needle of a compass. So the thing that is interesting is that the magnetic field that emanates from moving charges produces a force that acts at a right angle to the current flow. So the electric field produces motion for charged particles parallel to itself, or anti-parallel. If it's a positive charges would move one direction, negative charges move the other, parallel and anti-parallel. But a magnetic force, which comes from a magnetic field, which comes from moving charges. So a line of moving charge, if it's going that direction, it's producing magnetic field at a right angle to that motion. So rings of planes of magnetic field being emanated from those charges. So one of the things that they measured, so these pictures here, harder to understand. So here's a wire with moving current flow, and there's going to be these magnetic fields, so B, the obvious choice for magnetic field. Okay. Probably because of the Biot-Savart law. BIOT, we'll get to that in a second, and Savart people. So the letter inevitably comes from that. All right, so imagine over here in this wire, current's moving, and in fact, it would be moving this way. So if current's going the way that I've indicated with the arrow, you'll have this magnetic field that's curling around the wire. All right? And the only thing that can feel a magnetic force would be a moving charged particle, and moving charged particles cause that force. All right? So our visualizing here, this just kind of on the left here, just experimental fact. So here's this Biot-Savart law. I'm not going to derive it, just going to state it. Okay? And we'll get around to using it, but let's talk about its pieces, parts. First off, mu naught. Remember we had epsilon naught for the electric field? Well, we have mu naught for the magnetic field. It's the magnetic permeability of free space. So in the same way that you thought of epsilon, which was just some capacity of space itself to tolerate electric fields, mu naught is a fundamental property of the universe, of space itself, to tolerate magnetic fields. Okay? You could just think of it, mu naught and epsilon naught would be like the viscosity of space. How thick is the oil or the water or whatever? How easy can I move through that space? Those would be a metaphorical ways to think of those fundamental constants, right? And there's always a 4 pi or something involved with it because we're dealing with spherical things, so we get that sort of thing going for us. But then there's this other part. So this QV cross product with the direction of motion. You may not recall, but one of the things that we showed in first semester physics was when you have forces or motion that interacts in a plane and it produces a motion or a force perpendicular to that plane, that means the mathematics that's associated with that is a cross product. You learned about cross products very briefly in a trig or pre-calculus course when you did some matrices, Kramer's rule. We showed that with torque in the first semester. And so we have dot products, which is what we've been working on with potential energies work, and then a cross product, it applies because we're dealing with a field effect that's produced at a right angle. So if the effect is at a right angle to the cause, there's a cross product involved. That's the short story. And so the Biot-Savart law is a cross product. Okay, and so a dot product is a magnitudes times the cosine of the angle between. A cross product is a magnitudes times the sine of the angle between. That's the algebra that boils down to it. And interestingly, notice that we have this per r squared business. Notice how Coulomb's law has a constant per r squared for the electric field. Well, the Biot-Savart law still is an inverse square law, except the nature of what's happening in the top is different. In Coulomb's law, it's just charge, but in the Biot-Savart law, it's charge speed. So that's the thing that we notice is that that charge has to be moving for there to be a magnetic field associated with that charge. If the charge is not moving, there will not be a magnetic field associated with it, because V will be 0. Right? And things are still pointing. You know, you still have your unit vector, and it's stuck in here too in the cross product. It's a little weird. So Coulomb's law is simpler to look at because it's purely algebraic. There's no vector products to mess with, whereas it's a slightly more complicated, but if you kind of step back and look, it has essentially the same structure. It's still an inverse square law. There's a constant associated with it. And then the charge, instead of just charge alone, it's charge times speed. Moving charges produce magnetic fields. So if you've ever seen the Northern Lights, then you've seen the effect of moving charges interacting with a magnetic field, namely protons from the sun, the solar wind, if you will. The sun is spitting out an enormous amount of protons per second that bombard our planet, every planet in the solar system. And planets that have magnetic fields, which Earth is one of them. When a charged particle interacts with that field, what happens is it starts to deflect it. And so the Northern Lights are these charged particles that are spiraling in, and in the process of that energy transfer, they emit light. Short story on the Northern Lights. So you've seen the Biot-Savart law. If you've seen the Northern Lights, you've seen the Biot-Savart law. You've seen the result of what this law describes. All right? Part of the story. All right, so let's get back to this thing. So we've obtained, in the prior lecture, a drift speed equation. We related it in this lecture back to the electric field. We took a little break and showed how the magnetic field part, and we'll come back for more in magnetic stuff. But so let's get to electron current. Okay, so here you have, here's that mobile sea of electrons. Okay, remember electrons, they move opposite the field that's applied. So in some little time chunk, this mobile sea will move a distance, because this right here that's just the first zeroth law, V delta T. It moves some distance. Right? Oh, I just noticed I have my deltas in a subscript location instead of where it ought to be. To fix that slide. V delta T. It's moved some distance in that time. And this distance is a volume. So there's a volume that's moving in that. So here you have the area, which is this bottom of the can, if you will. And here's the length. This is a volume because it's area times length. Cylinder, volume of the cylinder, be the area of the base times the height of it. It's really all we have done in this picture. So now we are taking advantage of the geometry of the situation and seeing where that leads us. So volume, big V for volume, not voltage or speed. Okay. So here's this little thing here. The density of the mobile electrons in that volume. So guess what? Every conductor will have a different density number. And I'm not talking about the density of the material itself. We're talking about the density of the mobile electrons. How many are packed into that space? You know, how do they cram all those grams, so to speak? We're just going to call it in. Okay, the mobile electron density number. All right? And it would just be so this number n kind of just comes into what we just worked out. Okay, here's the volume. Okay, and then our rate. Okay, that's where that T comes in. So we're just kind of building our formula here. And we come up with this in the density of the mobile electrons, the drift speed, and the cross-sectional area for that flow. So if you remember, back a few slides, we had just a 2D version, and we had said, you know, how many electrons are moving past a point or a line in the sand? We just taken that line and stretched it to a 2D. Then that area, now we're talking about an area as a cross-sectional area, which is a line through a volume. It's a section, a conic, kind of that kind of thinking way to go. And so now I have a way to talk about the rate of current flow in terms of the density of the mobile C itself. Time got wrapped up in the average speed. Obviously, it deals with the time factor. But it's also now that area is dealing us with a place, a location through a flux, if you will, for that. And so we get to, finally, the definition of electron current, little I, is going to be that density number for the conductor we're dealing with, the cross-sectional area for flow, so it's a thicker wire versus a thinner wire. Okay? So it's like if we went out in the hallway here. It's a big hallway. A lot of room for student flow. Okay? If we went to the library building where the hallways are smaller, not as much room for student flow. But if there's a lot of students there, that will change the flow rate of students in either place. But they have their different capacities because of the size, the cross-sectional area that's available for motion. That's how to think about that A part of the puzzle. But remember, drift speed from our the first thing we derived today was this electron mobility times the electric field. Because guess what? We don't really we don't have an easy way to measure the average speed. It's not like we have a radar gun for electrons, okay? They're moving too fast, they're too small, there's too many of them. But what we can do is know what the electric field applied to a wire or some conductor is. And every material has its own electron mobility number, little u. So therefore we can actually know, given that we know what field we're applying to a conductor, u, the electron mobility, is a constant per conductor, copper, steel, aluminum, etc. The cross-sectional area, something I know the gauge of the wire. I could get out a micrometer and measure its diameter, and I would know the cross-sectional area, right? And then the density number is a material property. So N and U are material properties. A is a geometric property, cross-sectional area, and E is a variable I control, how much voltage the electric field is going to be proportional to the voltage. Okay? And we can control the voltage that's applied. So we get to our number. All right, let's deal with a problem here. I apologize. There are some metals, like these two here. Some things called semiconductors, which all the circuits and stuff like in your phone are semiconductors. And they behave strangely. In fact, their behavior as if the positive holes are moving. It seems that way. We won't really see it in this course because we won't deal with semiconductors directly, but we'll talk about it. And I think we already talked about how the fact that Franklin 50-50 got it wrong. He should have named the positive negative and the negative positive, and we wouldn't have electron flow, which is electrons moving one way, versus what's called conventional current flow, which is pretending that the positive things move. In fact, we saw that in the simulation video before the break. All right, so I want to probably review that. All right, so here's this change, if you will. Capital I for conventional current, right? And it's the magnitude of the charge in that NIV, or just magnitude of charge times our electron current flow. So basically it's making it positive, which would turn it around. And so thankfully they're equivalent. Even though the electrons are going the opposite direction, your current flow is still the same magnitude. And you can pretend that it's the holes moving. So electrons are going one way, and the spaces between them are the holes. We go into just a different view. So we've tolerated that because no one had the nerve to just say, look, we made a mistake, let's switch it. All right, that's where we're at today. Now here, in a short length delta L of wire, there would be in a delta L. So we just did this once, so let's not pretend that it's perfectly clear. N was the density number of mobile electrons. It's going to change for each material. This right here is just a volume term, right? Area times length, the volume term. So inside of that volume, okay, we can put all of this together, if you will. And you end up taking your NaL, when you rearrange all these things, you can take the thing that's called I, all right, and it's just an equivalence here. Not really important. We're not going to use it much, if at all. Just a little factoid there. So here's, we already did this once, showed that earlier, of our law. I can change QV and I delta L are the same thing. That's the point there. We'll have a chance to compute the magnetic field using the Biot Savart law either form, and charge times speed is an equivalent thing to the current times the change in distance. So if you think about that, QV, some number of coulombs times meters per second, where I is some number of coulombs per second times a meter, right? So it's almost like we should have known. So QV has units of coulomb, so do this kind of unit analysis, and meters per second, which is a coulomb meter per second kind of thing. Down here, I delta L would be coulombs per second times meters, which is going to be coulomb meters per second. We almost didn't need to do the other derivation, because the idea is the current is a number of charges per second, okay? But the speed is meters per second. So it's these bracketed things, it's kind of just unit analysis notation there. Those would be the units of those things. So current has those units, length has those units, charge, speed. Here's a little, I guess, difference here. This form, many moving charges. And each one of those chunks produces, you know, this magnetic field. So you could think of tiny little chunks of delta L, and they're producing a magnetic field that's proportional to the charge speed in that area product. Now, you could perhaps bother with scribbling all of this down, but I think you would get more by just watching and listening. But if you want to, you can. So let's just kind of think about this long thin wire. So this tube here That's the long, thin wire that we're going to analyze. And here is a little chunk of current that we're going to pay attention to in that wire. And relative, so out here at some point that we want to pay attention to, there's an x distance that it's away and a y distance, which means Pythagoristically, we got us a right triangle going on here. So there's a lot of math on this page. I didn't set it to go one at a time, so you just have to kind of ignore it as we go. So this position here, this would be our x that you can see up here. So it's x and then no y and no z. Okay? And that's where this is coming from. And then you have another position up here. You know, that's our y. And so the vector, the position vector, that's what r is. The position vector is going to be the difference between those 2 points. Because this is an x vector, this would be a y position vector, way to think about it. And so now I have a relative difference here. So you just get this, and it's just the rectangular coordinates. This position vector is an x, y position vector, minus y because of where it's located, no z. So if we do Pythagorean's theorem, square root of the sum of the squares, we get this right here. Really didn't need, we should know that by now. Okay, x squared plus y squared is going to be r squared. Therefore, r is the square root of that sum of squares. And then the unit vector would be taking your actual r vector, this right here, dividing it by your magnitude, and that's what your pointer is. That would be the structure of your pointer. So if you knew these lengths, you'd get a number for the numbers in the unit vector versus this symbolic mess that we're looking at. So that's that. Now, let's talk about delta L, this thing right here, little chunk. Where's it at? Well, it's at, if we wanted to actually, this looks like it would be a, yeah, give it a 1 right here. So delta L gets to pile into here. The notice that we should write the original law, delta B, would have been the mu naught per 4 pi, and then you'd have I delta L cross with the r pointer over r squared. So this right here is r squared. Take this thing and square it, it has no more square root. So that's why that works out this way in that part here. So all we've done is put r squared in, which is no more square root involved here. So you have all of this stuff. You go through this math, and this would be a way to compute that changing magnetic field in terms of the current flow, which we would know, because we could, I want to put an amp, or half an amp, or 10 amps of current through that. X and Y those are links, but they're positions. Again, so now I have a geometric thing that piles into here, things I can measure. I can measure X positions and Y lengths and whatnot. I can decide what the current flow is going to be, okay? And so 4 pi is a constant, mu naught's a constant. So that means, and we've done this a bunch of times where we've taken something that was kind of this weird energy force thing, but it ended up being just a geometric, like capacitance. Ultimately is about the area and the separation distance. And that's unexpected. And here, the magnetic field, we've pitched it all in terms of things that can be controlled or measured by us. Because we can't really talk about the speed of an electron in the QV version of the Biot-Savart law. Now, if we assume it or know the speed somehow, for some other reason, that's different. But this one gets us to the utility of this is going through all of this math to get to something that says, oh, these are inputs I can measure and control. And ultimately in science, we're constantly looking for that. So the utility of this page isn't so much that I'm going to ask you to do this on the exam, it's just showing us how does the process of science deliver something that is usable. And you have to go through this mathematical stuff to obtain things that are useful. Somebody's got to do the math so that somebody else has a useful tool that's practically useful outside of a physics classroom, okay, or a physics research evil lab. So here's a calculus version of computing that, and I'm gonna skip on past that. That's just coming from the geometry, the calculus of that. Now, not going to derive these, but notice there are some changes depending on what we're dealing with. So, circular loop, so there's, depending on where I'm at with a circular loop, so it's one circular loop, but things are different. So if I'm at some point Z out here, okay, how is this going to work out? But what I want to do first is I want to show we have a 2I per R when you're at the middle, and you have a 2 pi I when you're at Z. Okay, so let's, in fact, I'm gonna need to erase here. So they have that 2 pi I in common. The constant is in common, but what's different is you have this R squared and this weird Z squared plus R squared, which should be unsurprising because what are we dealing with again? We're dealing with another triangle, right? We're out here, we're up here. We're going to have, what's different here though is that it's to the 3/2 instead of the 1/2. 1/2 would be that square root. So there's something complicated about this loop, okay, that was different than just a two-dimensional straight line. Okay, so that cube thing is coming from ultimately the calculus, okay, that would be adding up all of these contributions in 3D space because we have a contribution here and there and there and there and there. So it gets complicated really fast, yeah.
So taking the denominator to the 3/2 power was referenced in the last slide too with the triangle. What was the reference on that?
It's not really something that we're covering in the course. Here. All I'm pointing out is there's a little bit, there's a lot they have in common. So this super simple when we're at the middle of the loop, where there are no angles, is nice and simple. But then when we're out at the displaced from the center but along the axis, now I get this gobbledygook that comes from the the fact that we're gonna triangle things, but the thing that's different here is in the first one, where we had the square root of that in the bottom, that's because it was just a straight line. We had one triangle per delta L, and they were all along the same dimension. Now I have just all these other angles in 3D space. So that's why it's more complicated in that regard. But again, for us, we just would look up the formula and use it. We're not going to derive all of these formulas. There's too many formulas to derive in that regard.